In this section, let's talk about max or min of a function, sort of continuing from the previous section on the increasing decreasing function. We started that a little bit. It's kind of a very similar idea. If a function has a relative maximum, we'll distinguish it with absolute maximum a little bit later on. But a function has a relative maximum at x equals c, let's say, let's pick a value, if f of c, the y value, is greater than or equal to f of x for any x in sort of like a small open neighborhood around it. You can sort of see it in the picture. Here, the maximum may not certainly be the biggest y value of a function, but it's bigger locally or nearby. Notice sort of like it's top of the hill, or it kind of looks like it. So there's a value c to which the y value is the largest for the values nearby, for some small neighborhood we call it, or interval AB. And minimum is very similar. Again, I like to think of it as peaks and valleys sort of all. See how you have it in the bottom right here. Again, it's the lowest, maybe not the lowest y value, but it's the lowest one nearby, again on the open interval AB. And how do we find if a function has any relative max or min points? It's very similar to what we started last time. What we can use is something called first derivative test, which later on we'll see with a second derivative test how it looks like. Let's scroll down a little bit. So what's happening? First, let's find critical numbers of f of x. If you recall from last time, critical numbers of f of x are where the derivative is 0 or undefined as long as the original f of x is defined at that point. And then we test critical points or numbers on the number line, just like we did last time. And we can kind of tell that f of x has a relative max if your sign switches from positive to negative. Again, we're plugging in those values into f prime of x because the derivative of the tangent, slope of the tangent line is positive. It goes from increasing, as you can see, up to 0 or undefined to decreasing or negative. So if it switches from positive to negative, again, I usually don't memorize it. I kind of draw it out for myself so it looks like a maximum. Or f of x has a relative min if, again, if we switch from negative to positive, if it stops decreasing and starts increasing. Or what can happen is no extrema, where you don't have a change in sign. It goes from positive to positive or negative to negative. How does that happen? Well, if you have this sort of inflection point, this is what we call it. Notice how function was increasing, then it slowed down temporarily, and then it starts increasing again. So it doesn't really change sign, but it's sort of like hits a plateau point or an inflection point. So we don't have an extreme in that case. So again, now we can find any relative extreme of any function without even graphing it. This is how cool the derivatives are. So that's kind of interesting. So let's start with a relatively easy function, a quadratic function. We can find critical numbers by taking the derivative. So we have 2x minus 10. Notice it's always defined because it's a polynomial. We can set it equal to 0. Usually I try to do this separate. Solve for it. It's x equals 5. So let's test it on the number line. And this is how I usually draw it out. Here is a number line. I write 5. Then I pick a couple of test points, something easy like 4 and 6, for example, to plug into the derivative. So then I write f prime of x and f of x right below it. Notice I plugged in 4 into 2x minus 10. So you'll get negative 2. Notice, so f prime of x is negative, which means f of x is decreasing. And then if you plug in 6, you're going to get 12 minus 10, that's positive 2. So you'll get plus for f prime of x, which means the original function is increasing. So what do you have? It looks like a little min if you kind of join your arrows, or notice how arrow sort of dips down and then goes back up again. So we have a minimum at that point. So f of x has a relative min at x equals 5. Now how we present an answer, the final answer, is because the min value is the y value. What we have to do is plug it in into the original function f of x, and I got 8 when I plugged in into f of x. So now we're done with the derivative. So how we can write it either as a point 5 comma 8, or also you can write 8 or y equals 8 at x equals 5. Okay, so we have a relative min. Same idea with a cubic function right here. So we take the derivative. You can set it equal to 0. So notice you get a quadratic. I pulled out a 3, but I keep it there when we test it. And we factor it. So notice how you'll get x equals -3 or x equals -1. Again, we'll plot them on the number line to test them. And again, I usually plot from smallest to biggest, so -3 first and -1. Remember how we get 4 intervals? So I picked 3 intervals. So I picked 3 test points, -4, -2, and 0, something easy. And again, I will plug it into the derivative. And this is what I got, positive, negative, positive. The sign does switch, so it means function is increasing and then decreasing, so we got a max. And here it's decreasing and then increasing, so we got a min. And so we have relative max at -3. Again, how I got the y value, plug it back into the original f of x. So it's -3, -8, and we get relative min, -1, -12. Usually, the max value, the y value, is larger than the min value, but that's not always true, however. Like with rational functions, that's not always true. So we still have to plug it in and find out. Here is another example. Let's try a rational function. Let's say x minus 1 over x. We do have a vertical asymptote at x equals 0. Let's keep that in mind. Before taking the derivative, I rewrote it as x minus x to the -1 power. And that's a lot easier to take the derivative with exponents. And then you take the derivative, so get 1. And derivative of -1 comes down, becomes plus x to the -2 power. Remember how we decrease power by 1? Which is 1 plus 1 over x squared. It's easier to write it this way when we set it equal to 0 later. So, what do we know? The derivative is not defined at x equals 0 again, but it's not a critical number because f of x is also not defined. So remember, vertical asymptotes, you have to count them for the number line to put it in, but they're not critical numbers. Can we set it equal to 0? Well, there's a problem here. 1 is positive. 1 over x squared can also only be positive. So how can we ever get 0? Not possible. Even if we try solving for it, you'll get x squared equals -1, which is not possible, at least not with the real numbers. So we don't have any critical numbers. So if we don't have any critical numbers, it's not as before. We don't need to test it for increasing or decreasing. If there are no critical numbers, there are no candidates for extrema of the function. So there is no extrema. If you recall, with rational functions, it's very easy not to have any max or min. Sometimes, okay, but here on the next example we will have some extrema. We will have some critical numbers. So let's take a look. There is a vertical asymptote at x equals 3. Remember, we always need to note that. Then I use quotient rule to find the derivative, so you can try this for yourself. When you simplify this, this is what I got. So you can set it equal to 0. Remember how you can multiply by denominator on both sides. So it's really only the top that counts for the critical numbers. So we have x squared minus 6x plus 5 equal to 0. We can factor it. And here I got a couple, x equals 5 and x equals 1. These are critical numbers. Remember, x equals 3, this is where the function is not defined, but that's just a vertical asymptote, so not critical number. Oops, went too far. Let me backtrack. So how do we test them? Here I put 1. Recall how we have to put vertical asymptote, 3, and then 5. And then I picked test points 0, 2, and 4, and 6. So we have 4 intervals here. And we plug them into the derivative. I actually plugged that into the original derivative with x minus, let me write this out. F prime of x, let me rewrite it again. F prime of x, so write this out for yourself. You'll have x minus 5 times x minus 1 over x minus 3 squared. Notice the bottom we don't have to worry about so much because it's squared. It's always going to be positive. But just to keep it in mind. So if you plug in 0, that's -5 times -1 that becomes positive on the top, positive on the bottom, so we'll get plus. 2, on the other hand, will have negative 5, I believe, is negative, but minus 1 is positive, so on the top you'll get negative, so the whole thing is negative. And 4, same idea, you'll get negative, but 6, everything is positive, so we'll get a plus. But we have, looks like we have a max at 1, notice how I drew it out with the original function, but min at 5. And at 3, that was just a vertical asymptote, the sign did not change, but it doesn't matter. So we do have relative max. I plugged in 1 into the original function. I get 0 because I think it's x squared minus 2x plus 1. You get 0. And notice how max, the y value is smaller than the min, but that can happen a lot with rational functions. If it looks something like this, for example, I'm not saying it does, but this is just an example, you know, with a vertical asymptote, let's say, and the horizontal asymptote. Notice how here is a min, here is a max. Max is lower than a min, so that happens a lot. Okay, let's move on. Now let's try with log functions. There's a couple of log functions on the homework. It works exactly the same as previous section. So derivative would be basically 2 plus, recall, derivative of ln of x is 1 over x. F prime of x is not defined at x equals 0 because x is in denominator. But the original function is not defined at 0 either. Remember, ln of x is not defined at 0. So we don't have to worry about it. It's not a critical number. Can it ever be 0? Actually, it can because it's just 1 over x. Notice how I moved it over. And so I'm getting 2. Here we can multiply by x on both sides. I'm getting 2x equals negative 1. So x equals to negative 1/2. But the domain of the function is only positive numbers because remember, ln of x is not defined at negative 1/2. So even if we get something, since it's not in the domain, since it's only defined when x is positive, then we don't have to test it. F of x has no extreme point. So sometimes something strange like this occurs. So you have to pay attention to the domain of your function a little bit. Here is another one. Here is a profit with a ln function. Here we may have to use chain rule. And again, pay attention to this restricted interval. X is from 0 to 10, even though ln is not, actually it can be defined at 0 because ln of 1 would be 0. So it's 0 to 10. How do we find the derivative? Well, remember, it's 1 over that whole cubic expression times the derivative of that. So that's negative 3x squared plus 6x plus 72. If you remember the shortcut, the derivative goes on the top, the original function on the bottom. Okay. That denominator worries me a little bit. It probably can be 0, but since the original function is not defined at 0, we don't have to worry about it. It's not going to be a critical number. But the top can be 0 also. Notice we can set the whole function equal to 0, get rid of the denominator. So let's worry about the top. Looks like we can factor it. And once we factor it, we get two critical numbers, x equals 6 or x equals negative 4. But remember, negative 4 is not in the domain 0 to 10, and the function may not be defined that. So we're only testing x equals 6. Okay. And also makes sense because number of units can only be positive, so it doesn't make sense otherwise. So I tested 6. I plugged in 5 and 7 into the derivative. I actually did plug it into the denominator first, both for 5 and 7. But then on the top, I think I get positive in the denominator for both 5 and 7. But the top, notice how if you plug in 5 minus 6, and then 5 plus 4 actually gives us negative because it's negative 1 times 9 or something like that. But remember, there's negative 3, which is why we try not to get rid of the constants. Negative 3 is going to make it positive because negative times negative is a positive. 7, on the other hand, is going to give us both positive, but times negative 3 is going to give us negative. So do not forget about those factors, especially if they're negative. They can make a difference. Okay, so it is a maximum. Remember, plus means increasing, minus means decreasing. So 6 is a max. It's a good idea to test it. And then part B asks us what is maximum profit. That's sort of like finding the Y. So I plugged it in. I plugged it in into a len of, and I plugged in 6. I just plugged it in as is on the calculator, and I got 5.784. But I believe we had thousands in the original. Let's see. The total profit in thousands of dollars. So as usual, when the units do not match, so we have 5.784 thousand multiplied by 1,000, so I'm getting 5784. So that's the actual profit, and that's it for this function, for this video.